Right now, 4 billion miles from where you are sitting, in a place so cold that nitrogen freezes into solid rock and methane becomes ice harder than steel, something extraordinary is drifting through the darkness. Not one thing, thousands of things worlds. Frozen, silent, untouched for billions of years, some carry mountains that dwarf Everest. Some spin so violently they have stretched into impossible shapes. Some may harbour hidden oceans locked beneath shells of ice, oceans that have existed in total darkness since before the first living thing appeared on Earth. And some are so perfectly preserved they look exactly as they did on the day the solar system was born. Out there, the sun you know, the one that warms your face and fills your sky, has been reduced to nothing more than a cold, sharp point of light, no larger than a star, no warmer than starlight, and beyond that faint glow lies a wilderness so vast it makes the entire familiar solar system look like a campfire at the centre of an endless frozen night. Scientists call it the Kuiper Belt, and what they have found there is forcing us to rethink everything we thought we knew about where the solar system ends, and what kinds of worlds can exist in the deep cold beyond the light. If that sounds like the kind of journey you want to take tonight, do me a favour and hit that like button and subscribe. It keeps this channel going and helps us explore the mysteries that matter most. Now get comfortable, close your eyes if you need to. What follows is a story 4.5 billion years in the making, and we are going to walk through it together, slowly, carefully, all the way to the edge of the abyss and back. Let's begin. Right now, without moving an inch, without leaving the chair where you are sitting, you are a member of a solar system that is almost nothing like the one you were taught in school. The version you learned had a neat logic to it, a bright sun at the centre. 4 rocky planets close in, 4 gas giants farther out, a scattering of asteroids between Mars and Jupiter, and then, at the very end, small and distant and cold, Pluto. The diagram fit on a single page. The planets were spaced at roughly even intervals, their names printed in clean font beneath them, and the whole picture carried the quiet confidence of something finished. Something known. Something complete. That picture was never true. What actually exists beyond Neptune, beginning right where that familiar diagram fades into white margin, is a region so vast, so physically extreme, and so poorly represented in human imagination that encountering it honestly for the first time feels less like learning something new and more like discovering that the house you have lived in your entire life has an entire wing of rooms you never knew existed, stretching off into the dark in every direction. Scientists call it the Kuiper Belt. Begin with simple geography. The Kuiper Belt is a broad, donut-shaped zone of frozen objects that starts near Neptune's orbit, at roughly 30 astronomical units from the Sun, and extends outward to at least 50 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, approximately 93 million miles. So the inner edge of the Kuiper Belt sits about 2.8 billion miles from the Sun. The outer edge, at 50 astronomical units, lies roughly 4.6 billion miles away, and certain objects associated with the belt, members of what scientists call the scattered disk, reach out to 70, 80, even 100 astronomical units before their orbits turn back. These are not numbers that scale comfortably against anything in daily human experience. If you drove a car at highway speed toward the inner edge of the Kuiper Belt, without stopping, without sleeping, without ever slowing down, you would need to maintain that pace continuously for over 5,000 years just to arrive. The outer edge would require another 2,000 years of driving beyond that, and you would be driving through a perfect vacuum in total darkness, watching the sun shrink behind you from a warm disk into a cold, brilliant point no brighter than a distant star. But the raw distance is not the real shock. The real shock is what the Kuiper Belt does to the proportions of the solar system you thought you understood. Consider the familiar part again. Mercury orbits at roughly 1/3 of an astronomical unit from the Sun. Venus at about 7/10, Earth at 1, Mars at 1.5, Jupiter at 5.2, Saturn at 9.5, Uranus at just over 19, Neptune at 30. The entire sweep of planets from Mercury all the way out to Neptune covers approximately 30 astronomical units. That is the solar system with all the names, all the missions, all the photographs on magazine covers. Now look at the Kuiper Belt. Its main body alone spans from 30 to 50 astronomical units. That is 20 additional astronomical units of structure bolted onto the end of the solar system, in a region most people have never heard described in any real detail. And if you include the scattered disk objects dynamically linked to the belt, but travelling on wider, more eccentric paths, the Sun's outer frozen domain stretches to 100 astronomical units, or beyond. That means the icy outer zone is at least as wide as the entire planetary system, and possibly far wider. The solar system you know, the one with the rocky planets and the gas giants and the beautiful tilted rings of Saturn, fits inside the inner third of the Sun's actual domain. Everything beyond Neptune is larger in reach, and almost nobody talks about it. This is not a matter of recent discovery buried in obscure scientific journals. The Kuiper Belt has been a confirmed part of solar system science for over 3 decades. But even confirmed facts can be invisible if no one shows them to you in a way that lands. And the way the Kuiper Belt has been presented, when it has been presented at all, has consistently failed to communicate its true character. Think about every diagram of the solar system you have ever seen, on a classroom wall, in a textbook, on a museum display. The planets appear at roughly even intervals. The distances are compressed to fit the frame. Neptune sits near the right edge, and sometimes there is a faint dotted arc labelled Kuiper Belt just beyond it, small enough to seem like an afterthought, a footnote, a technical detail for specialists. The diagram stops there. The white space beyond it implies nothing. But that white space is not nothing. It is one of the most populated, most ancient, most scientifically valuable regions in the entire solar system. It contains more individual objects than the asteroid belt between Mars and Jupiter. It spans a volume of space so enormous that the asteroid belt could fit inside it thousands of times over. It holds frozen worlds with mountains and glaciers and possible hidden oceans. It preserves, in a state of nearly perfect suspension, the original building material from which the planets themselves were assembled 4.5 billion years ago, and it is almost completely absent from the mental model that most human beings carry of their own cosmic home. The asteroid belt, sitting between Mars and Jupiter at roughly 2 to 3.3 astronomical units from the Sun, is composed primarily of rocky and metallic objects. Silicate minerals, iron, nickel, materials that survive the warmer temperatures of the inner solar system. Even its largest member, Ceres, measures only about 940 kilometers across and was reclassified as a dwarf planet. The total mass of the entire asteroid belt is remarkably small, roughly 4% of the Moon's mass. Despite its dramatic appearance in science fiction, it is sparse and light. The Kuiper Belt is a different kind of place entirely. Its objects are built from frozen volatiles, water ice, methane ice, ammonia ice, nitrogen ice, carbon monoxide ice. These are materials that only hold their solid form at the brutally low temperatures found beyond Neptune, where the Sun's energy has faded to almost nothing. Surface temperatures on Kuiper Belt objects hover between -220 and -240 degrees Celsius. At those temperatures, methane, the same gas that heats your stove, becomes a pale crystalline ice. Nitrogen, which makes up 78% of every breath you take, freezes into a translucent solid. Carbon monoxide, a gas on Earth, locks into a rigid frost. These ices are not incidental details. They are the defining signature of the Kuiper Belt, and they point directly to why this region matters so deeply to science. The frozen materials out there are not random debris. They are the leftover ingredients of the solar system itself, the pieces that never got the chance to become part of something bigger, preserved in a state so close to their original condition that studying them is like finding the raw ingredients of a recipe long after the meal has already been eaten and the kitchen has been cleaned. The Kuiper Belt is not a barren edge. It is an archive. A frozen library built 4.5 billion years ago, sitting in the dark, waiting. And we have barely begun to read it. There is a particular kind of courage required to search for something you cannot see in a place you cannot reach, using instruments that sit at the very edge of their own capability, with no guarantee that anything is actually out there at all. That is exactly the situation two astronomers placed themselves in during the summer of 1987. Their names were Dave Jewett and Jane Liu. They were working at the University of Hawaii, using telescopes positioned high on the volcanic summit of Mauna Kea, one of the best observing sites on the planet. And the task they set for themselves was, by any honest measure, almost absurdly difficult. The theoretical case for a belt of icy bodies beyond Neptune had existed for decades. In 1951, astronomer Gerard Kuiper proposed that a disk of material might have existed in the outer solar system during the solar system's early history, though he suggested it had since been largely scattered away. Around the same time, Irish astronomer Kenneth Edgeworth independently suggested that a reservoir of small icy bodies might occupy that same distant region. The zone carries both their names in scientific literature, sometimes called the Edgeworth-Kuiper Belt, in recognition of both contributions. But a theoretical suggestion is not the same as physical evidence. For 40 years after those proposals, no one had detected a single object in that region beyond Pluto itself. Pluto, discovered in 1930, had been classified as the 9th planet and treated as a lone, cold outpost at the very end of the solar system. The idea that it might be one member of a much larger population was considered plausible by some researchers, but entirely unproven. The telescopes of earlier decades simply lacked the sensitivity to detect the kind of objects that would populate such a belt. Kuiper Belt objects reflect very little sunlight. They are small, dark, and unimaginably far away. Even a body several hundred kilometers across appears, from Earth, as nothing more than a barely perceptible point of light shifting almost imperceptibly against the background stars over hours or days of careful observation. Jewett and Liu decided to find out whether anything was actually there. Their method was elegant in its logic and punishing in its execution. They would take deep, long exposure images of small patches of sky near the plane of the solar system, then compare images taken hours or nights apart. A background star stays fixed. A solar system object moves. If a faint point of light shifted position between images at exactly the rate expected for something orbiting beyond Neptune, that moving dot was a candidate. A stationary dot was just another star in an already crowded field. The challenge was that the objects they were hunting were extraordinarily faint. A typical Kuiper Belt object sits millions of times dimmer than what the naked human eye can detect on a clear night. Finding one required staring at small patches of sky for long periods, collecting enough photons from these distant frozen bodies to register above the noise threshold of their instruments, and then doing the painstaking comparison work of distinguishing genuine movement from optical artifacts, cosmic rays, or instrumental errors. Night after night they scanned and compared, patch after patch of sky, exposure after careful exposure. The early results were discouraging in a way that would have defeated most researchers. Nothing moved. The outer solar system appeared to be exactly what conventional thinking had long suggested: empty. Year 1 produced nothing. Year 2 produced nothing. By year 3, the absence of any detection was loud enough to make a reasonable scientist question whether the whole enterprise was worth continuing. They continued anyway. Year 4. Year 5. Still nothing of significance. 5 full years of meticulous, patient searching in the cold dark above the observatory, 5 years of comparing images and finding only stars, produced 5 years of nothing. The theoretical belt remained theoretical. The outer solar system remained stubbornly silent. Then came the night of August 30th, 1992. A faint object, barely visible even in their long exposure images, was shifting position against the background stars. Not randomly. Not in a way consistent with a nearby asteroid or a known object. It was moving at precisely the rate expected for something orbiting the Sun at approximately 44 astronomical units from its centre. It was not an asteroid. It was not a comet with a visible tail. It was not a known planet or moon. It was something new, something occupying the exact region of space where the theoretical Kuiper Belt was supposed to exist. They designated it 1992 QB1. That single detection changed everything. Not dramatically, not immediately, but permanently. A door had been opened, and there was no closing it again. Within months, Jewett and Liu found a second object. Then a third. Other research teams joined the search, bringing their own telescopes, their own survey strategies, their own newly built CCD cameras capable of detecting fainter and fainter objects with greater efficiency. Within the next decade, improved technology and dedicated survey programs revealed a population of outer solar system objects that nobody had ever directly observed before. Hundreds of new bodies appeared in the data, each one a faint, slow-moving speck drifting through the darkness well beyond Neptune's orbit. The Kuiper Belt crossed from theoretical to undeniable. As of today, astronomers have catalogued over 3,000 Kuiper Belt objects, and the estimated total population of objects larger than 1 kilometre across is in the hundreds of millions. Models of the belt's structure suggest there may be more than 100,000 objects larger than 100 kilometres in diameter alone. The belt is not a sparse scattering of a few icy rocks. It is one of the most heavily populated structural zones in the entire solar system, containing more individual objects than the asteroid belt between Mars and Jupiter, spread across a volume of space so enormous that the asteroid belt itself could fit inside it thousands of times over. What makes this discovery so significant is not just the number of objects found. It is what their existence revealed about the nature of the solar system itself. Before 1992, the outer solar system beyond Neptune was a blank, a theoretical space, a mathematical boundary, a region that science acknowledged but had never touched with direct observation. After 1992, that blank began to fill. And what filled it was not a simple scattering of inert debris, but a complex, structured, layered population of frozen worlds, carrying within them the chemistry and physics of the solar system's very first moments. There is something quietly extraordinary about what Jewett and Liu did. They did not have the guarantee of success. They did not have a detection to guide them toward the right region of sky. They had a theory, a set of instruments, and the willingness to spend 5 years searching an apparently empty darkness without flinching. And the discovery they eventually made was not the discovery of one object in isolation. It was the discovery of an entirely new class of solar system body, an entirely new structural zone, and in many ways an entirely new understanding of where the solar system actually ends, or rather the discovery that it does not end where anyone thought it did. The door opened by 1992 QB1 has never closed. Every survey since has pushed deeper into that outer darkness, finding more objects, more complexity, more structure. And each new discovery has reinforced the same quiet truth. The solar system was always bigger than the diagram. We simply needed someone patient enough and brave enough to look. There is a difference between debris and a fossil. Debris is what remains after something breaks. A fossil is what remains after something stops. The Kuiper Belt is not debris, it is a fossil field. And what it preserves is nothing less than the original construction material of the solar system itself, frozen in place at the exact moment the planets finished forming and the leftover pieces were abandoned in the cold. 4.5 billion years ago, the Sun was surrounded by a vast rotating disk of gas and dust called the solar nebula. This was not a simple cloud. It was a structured, layered environment where temperature, pressure, and distance from the young star determined what kinds of materials could exist in solid form. Close to the Sun, where temperatures were scorching, only the hardiest materials survived. Rocky grains, metallic particles, substances that could withstand intense heat without vaporizing. These materials clumped together over millions of years, building the cores of the terrestrial planets: Mercury, Venus, Earth, Mars. Farther out, beyond a boundary called the frost line, conditions were colder. Cold enough for water to freeze, cold enough for methane, ammonia, and other volatile compounds to condense into solid ices alongside the rock and metal. This colder region became the feeding ground for the giant planets. Jupiter, Saturn, Uranus, and Neptune grew massive solid cores from a mixture of ice and rock, and those cores became gravitationally powerful enough to capture enormous envelopes of hydrogen and helium gas from the surrounding nebula. The result was the gas giants we observe today, each one a world whose visible surface is not solid ground, but the top layer of an atmosphere thousands of kilometers deep. But not everything in the outer solar system got incorporated into a planet. Beyond Neptune, the density of material in the solar nebula was lower, orbital periods were longer, objects moved more slowly, and the timescale required to assemble a large planet from scattered material stretched into hundreds of millions of years, far longer than the nebula itself survived. By the time the gas in the disk had dissipated, blown away by the young sun's radiation and stellar wind, the region beyond Neptune was still populated by countless small icy bodies that had never managed to coalesce into anything larger. These leftover pieces remained. And they remain still. The Kuiper Belt objects we observe today are planetary construction debris, not fragments from planets that shattered, not pieces knocked off something larger. They are original building blocks that never got the chance to become part of something else. They are fossils of the solar nebula, pieces of the cloud that birthed the Sun and everything around it, frozen in a state remarkably close to their original condition. This makes them extraordinarily valuable to science. Because the Kuiper Belt is so far from the Sun and so cold, these objects have been preserved with almost no alteration. The rocky planets underwent intense heating, melting, differentiation and resurfacing. The gas giants captured atmospheres and underwent internal rearrangement. Asteroids in the inner solar system were baked, battered, and chemically modified by solar radiation and collisions over billions of years. But Kuiper Belt objects, sitting in the frozen darkness beyond Neptune, experienced almost none of that. They stayed cold, they stayed dark, they stayed chemically intact. Studying them is like studying the ingredient list of a meal after the cooking is finished and the kitchen has been cleaned. The planets formed and evolved. The Kuiper Belt stayed raw. The composition of these frozen bodies tells the story directly. Water ice dominates most Kuiper Belt objects, but it is not alone. Methane ice, detected on the surfaces of Pluto, Eris and Makemake, condenses only at extremely low temperatures and preserves a record of the chemical conditions in the outer disk. Nitrogen ice, observed flowing in vast glaciers across Pluto's surface, is even more volatile and evaporates easily unless kept brutally cold. Carbon monoxide ice, ammonia ice, and complex organic compounds called tholins, reddish tarry residues formed when simple molecules are irradiated by cosmic rays and ultraviolet light, all appear in varying concentrations across the belt. Each of these materials points back to the same conclusion. The Kuiper Belt preserves chemistry from the solar nebula with minimal processing. These are the same ices that once coated the cores of the giant planets before those cores grew large enough to capture gas. These are the same organic compounds that would later be delivered to the inner solar system by comets and possibly contributed to the chemistry that led to life on Earth. The Kuiper Belt is not a random graveyard. It is an archive of origin, a library holding volumes written in ice and organic carbon, stored at temperatures so low that the text has not degraded in 4.5 billion years. But the preservation is not perfect. There has been interference. The belt we observe today is not the primordial disk exactly as it formed. It has been sculpted, rearranged, and partially emptied by the gravitational influence of the giant planets, particularly Neptune. In the early solar system, the giant planets did not occupy their current orbits. They migrated. Jupiter moved slightly inward. Saturn, Uranus and Neptune moved outward, driven by gravitational interactions with the massive disk of icy planetesimals that surrounded them. Neptune's outward migration was the most dramatic. As it swept through the outer solar system over tens of millions of years, its gravity acted like a slow-moving plough cutting through a dense field of frozen debris. Some objects were flung inward toward the Sun, raining down on the inner planets in a bombardment so intense it resurfaced entire worlds. Others were hurled outward onto wildly eccentric orbits, populating what is now called the scattered disk. Still others were captured into orbital resonances with Neptune, locked into gravitational patterns that stabilized their orbits and allowed them to survive. The result of this chaos was dramatic. Estimates suggest that the Kuiper Belt today contains only a few % of the mass that originally occupied the outer disk. The rest was lost, ejected into interstellar space, sent crashing into the inner solar system, scattered beyond the reach of easy observation. What remains is a survivor population, a fraction of the original community that endured Neptune's migration and settled into stable orbits. This means the Kuiper Belt is simultaneously ancient and young. Its objects are ancient, composed of materials that condensed from the solar nebula 4.5 billion years ago. But the orbital arrangement of those objects is younger, imposed by Neptune's migration roughly 4 billion years ago during a period of violent dynamical reorganization. The objects themselves are old. Their addresses were assigned later. This distinction is crucial. It means the Kuiper Belt carries two kinds of information. The first is chemical and physical, what these objects are made of, what their surfaces look like, how their interiors are structured. The second is dynamical, where they orbit, how eccentric their paths are, whether they are locked into resonances or scattered into the outer reaches. The first kind of information tells you about the solar nebula. The second tells you about the chaos that followed planet formation. And what the combination reveals is a story more violent, more contingent, and more dramatic than the orderly diagrams of textbooks ever suggest. The solar system did not assemble smoothly. It underwent upheaval. Planets migrated. Entire populations of icy bodies were flung across billions of miles. The architecture we observe today is not the architecture that initially formed. It is the architecture that survived. The Kuiper Belt preserves both chapters of that story. It holds the original ingredients in frozen suspension, and it bears the scars of the chaos that reshaped the outer solar system during its violent youth. Every resonant cluster, every gap in the orbital distribution, every population of scattered objects is a forensic clue pointing back to events that happened over 4 billion years ago. Events that determined not just the structure of the outer solar system, but the delivery of water and organic material to the inner planets, possibly including Earth. The Kuiper Belt is not a graveyard in the sense of something dead and finished. It is a graveyard in the sense of something that holds memory. Memory written in ice. Memory locked in orbit. Memory waiting, patient and cold, for someone to arrive and read it. If you look at a map of the Kuiper Belt today, what you see is not random. The objects do not scatter evenly across all possible orbital distances. They cluster. They avoid certain regions entirely. They gather in groups that share suspiciously similar orbital characteristics, moving in lockstep patterns that repeat with mathematical precision. And all of this structure, every cluster, every gap, every resonant family, points back to a single architect. Neptune. The story begins not with the Kuiper Belt as it exists now, but with the outer solar system as it existed 4.5 billion years ago, shortly after the planets finished forming. The giant planets, Jupiter, Saturn, Uranus and Neptune, did not occupy the orbits they hold today. They were closer together, packed into a more compact arrangement, embedded in a massive disk of leftover icy planetesimals that stretched from roughly 15 astronomical units outward to 30 or beyond. This primordial disk was dense, thick with material, populated by trillions of small frozen bodies that had condensed from the solar nebula but never assembled into anything larger. The planets and the disk existed in uneasy gravitational proximity. Every time a planet passed near one of these icy bodies, it exerted a gravitational tug. Most individual tugs were tiny, but there were billions of objects and billions of interactions happening over millions of years. Those interactions accumulated, and they had consequences. Jupiter, the most massive planet by far, tended to fling objects inward or outward with tremendous force. Saturn, Uranus and Neptune also scattered objects, but the effects varied depending on the mass of the planet and the geometry of each encounter. Over time, the cumulative effect of all these gravitational kicks began to alter not just the orbits of the icy bodies, but the orbits of the planets themselves. The physics works both ways. A planet that flings an object outward experiences a tiny inward push in return. A planet that scatters an object inward gets pushed slightly outward. Individually, these nudges are negligible, but add them up across millions of encounters and the planets begin to migrate. Jupiter drifted slightly inward. Saturn, Uranus and Neptune drifted outward. The migration was slow, measured in fractions of an astronomical unit per million years, but it was relentless. And Neptune's outward journey had the most profound effect on the structure of the outer solar system. As Neptune moved outward, it ploughed through the dense primordial disk of icy bodies like a ship moving through thick fog. Its gravity interacted with every object it encountered. Some were flung inward, sent tumbling toward the Sun on chaotic trajectories that brought them crashing into the inner planets during a period scientists now call the Late Heavy Bombardment. The craters that scar the Moon's face, the ancient impact basins on Mercury and Mars, many of these were carved by icy projectiles dislodged from the outer disk during Neptune's migration. Other objects were flung outward, hurled onto highly eccentric orbits that carry them far beyond the main belt. These became the population we now call the scattered disk, objects on wildly elongated paths that spend most of their time in the distant outer reaches before swooping back briefly toward the Sun. And still other objects were captured. Trapped. Locked into something called orbital resonance with Neptune. A resonance occurs when two orbiting bodies exert regular, repeating gravitational influence on each other because their orbital periods form a simple numerical ratio. The most famous resonance in the Kuiper Belt is the 2-to-3 resonance with Neptune. Objects in this resonance complete exactly 2 orbits around the Sun for every 3 orbits Neptune completes. This creates a repeating pattern of gravitational interactions that stabilizes the smaller object's orbit, protecting it from close encounters with Neptune that would otherwise scatter it away. Pluto is the most famous member of this resonance. It orbits at an average distance of about 39 astronomical units, and despite the fact that its orbit actually crosses Neptune's orbital path on a diagram, the two bodies never come close to colliding. The resonance keeps them synchronized, separated in space even when their paths appear to overlap on paper. Pluto is not alone. Hundreds of other icy bodies share the same 2-to-3 resonance. Scientists call them Plutinos, and they represent one of the major dynamical populations within the Kuiper Belt. Their existence is direct evidence of Neptune's gravitational influence. Without Neptune's migration sweeping through the outer disk and capturing objects into resonance, Plutinos would not exist as a distinct group. Other resonances exist as well. The 1-to-2 resonance, where an object completes 1 orbit for every 2 Neptune orbits, holds a smaller population called Twotinos. The 2-to-5 resonance contains another group. Each resonance acts like a gravitational trap, a stable island in orbital space where objects can survive for billions of years without being scattered. Between the resonances lie gaps, regions of orbital space that are almost completely empty. These gaps exist because certain orbital distances correspond to destabilizing resonances, patterns that amplify gravitational kicks rather than dampening them. Objects that wander into these unstable zones get scattered away over time. The gaps are not voids in the physical sense, but they are voids in the population distribution, carved by Neptune's gravity as surely as a sculptor carves stone. Beyond the resonant populations lies the classical Kuiper Belt, objects on relatively circular low-inclination orbits between roughly 42 and 47 astronomical units. These objects appear to have avoided the worst of Neptune's gravitational disruption. They formed farther out beyond the reach of Neptune's migration and survived in orbits that have changed little since the belt's earliest days. Scientists sometimes divide this population further into the cold classical belt, with very low inclinations and eccentricities, and the hot classical belt, with higher inclinations suggesting these objects were gravitationally stirred at some point in their history. The sharp inner edge of the Kuiper Belt, which begins almost exactly where Neptune's orbit lies at 30 astronomical units, is no coincidence. Neptune's gravity swept the region clean. Any object that once orbited closer than 30 astronomical units was either captured into resonance, flung away, or ejected entirely. The inner edge is not a natural boundary formed during the solar system's birth. It is a scar, a boundary carved by Neptune's passage through the primordial disk. Every feature of the Kuiper Belt structure, every resonant population, every gap, every gradient in orbital inclination, points back to the same conclusion. Neptune is the architect. Its migration sculpted the belt into the form we observe today. Without Neptune, the Kuiper Belt would look completely different. The resonances would not exist. The inner edge would not be so sharply defined. The classical belt would blend smoothly into the scattered disk without clear boundaries. But Neptune's influence did more than rearrange orbits. It also determined which objects survived. The Kuiper Belt we study today is not the full primordial population. It is a remnant, a small fraction of what once existed, shaped by a selective process driven entirely by gravitational mechanics. Objects in stable resonances survived. Objects in unstable regions were removed. The architecture we observe is not the architecture that formed. It is the architecture that endured. This realization carries profound implications. It means the early solar system was far more violent and chaotic than the calm, orderly diagrams suggest. Planets did not form in place and stay put. They migrated. They interacted. They rearranged the entire outer solar system, scattering populations, carving gaps, and leaving behind a structure that serves as a permanent record of that ancient upheaval. Neptune did not intend to create the Kuiper Belt. It simply moved. And in moving, it sculpted one of the most complex, most informative, most scientifically rich regions in the entire solar system. Every orbit tells a story. Every resonance preserves a moment, and every gap marks the absence of something that could not survive. The Kuiper Belt is Neptune's unintentional masterpiece, a structure built not by design, but by the inexorable mathematics of gravity acting over billions of years. And we are only now beginning to read the blueprint. Pluto was never alone. For decades it carried the title of ninth planet, treated as a solitary outpost at the edge of the solar system, small and distant and cold. Textbooks placed it at the end of the planetary lineup, and the implicit message was clear. Beyond Pluto, nothing. The edge had been reached. The map was complete. That narrative collapsed the moment astronomers began discovering what actually surrounds Pluto. It is not an isolated world. It is a local. One resident among a vast community of frozen bodies drifting through the same distant region. And some of those neighbours are nearly as large as Pluto itself. A few are even more massive. The first major challenge to Pluto's uniqueness came in 2005 with the discovery of Eris. Located in the scattered disk far beyond the main Kuiper Belt, Eris has a diameter of approximately 2,326 kilometres, making it almost identical in size to Pluto. But Eris is slightly more massive, denser, carrying more material packed into a similar volume. Its orbit is wildly eccentric, swinging from about 38 astronomical units at its closest approach to the Sun, out to nearly 98 astronomical units at its farthest point. That outer reach places Eris well beyond the main belt, deep into a region so remote that sunlight there is reduced to a faint glimmer barely stronger than starlight. Eris has one known moon, Dysnomia, roughly 600 kilometres across. Its surface is covered in a bright frost of frozen nitrogen and methane, giving it one of the highest reflectivities of any object in the solar system. The brightness suggests a surface that is constantly refreshed, possibly by nitrogen ice that sublimates during the warmer parts of its orbit and then refreezes onto the surface as Eris moves back into the coldest outer zones. The discovery of Eris was the direct trigger for Pluto's reclassification. If Pluto qualified as a planet, then Eris, similar in size and more massive, had to qualify as well. Rather than expand the planetary roster indefinitely, the International Astronomical Union created a new category in 2006, dwarf planets. Both Pluto and Eris were placed in this category, along with Ceres in the asteroid belt and several other candidates. The decision was controversial, but the logic was clear. The outer solar system contains too many large icy bodies to call them all planets without rendering the term meaningless. Makemake, discovered in 2005 and named after a creation deity from Rapa Nui mythology, orbits at an average distance of about 45.8 astronomical units. Its diameter is approximately 1,430 kilometers. It has a surface dominated by frozen methane and ethane, with evidence suggesting the methane ice exists in large crystal grains, a detail that points toward long-term surface processing by weak ultraviolet radiation from the distant Sun. In 2016, astronomers using the Hubble Space Telescope detected a small moon orbiting Makemake, provisionally designated as a faint companion that had escaped notice for years due to its proximity to the much brighter primary body. Haumea is among the strangest objects in the solar system. It is not round. Haumea spins so rapidly, completing one full rotation in under 4 hours, that centrifugal force has stretched it into an elongated ellipsoid, shaped roughly like a flattened football. Its longest axis measures approximately 2,320 kilometers. Its shortest is considerably less. This extreme rotation is thought to be the result of a massive ancient collision that not only distorted Haumea's shape, but also produced a family of smaller icy fragments that share similar orbits, the only known collisional family in the Kuiper Belt. Haumea has 2 known moons, Hiaka and Namaka, both likely fragments from the same ancient impact, and in 2017, astronomers made a startling discovery. Haumea possesses a ring system, the first ring ever detected around a trans-Neptunian object. The ring orbits at a distance of roughly 2,300 kilometers from Haumea's center, a thin band of material held in place by the dwarf planet's gravity and rapid rotation. Quow, orbiting at about 43 astronomical units with a diameter of roughly 1,110 kilometers, delivered its own surprise. In 2022, astronomers using stellar occultation data detected a ring around Quow, located at a distance of roughly 4,100 kilometers from the object's center. This was shocking because the ring orbits well beyond what is called the Roche limit, the boundary inside which tidal forces should prevent material from clumping together into a moon. According to conventional theory, ring material that far out should coalesce into a solid body rather than remain dispersed as a ring. The discovery challenged established models of ring dynamics and remains an area of active investigation. More recently, in 2025, astronomers reported evidence suggesting Quow may have an additional moon, making it an even more complex system than previously understood. The exact nature of this potential companion is still being studied, but the finding underscores a broader pattern emerging across the Kuiper Belt. These distant frozen worlds are far more dynamic, far more geologically interesting, and far more complex than early models predicted. These 5 objects, Pluto, Eris, Makemake, Haumea, and Quow, are simply the most prominent members of a much larger population. Hundreds of other Kuiper Belt objects exceed 200 kilometers in diameter. Many of these have their own moons. Some likely possess complex surface compositions, mixtures of water ice, methane, nitrogen, and organic compounds. A few may even harbour subsurface oceans, thin layers of liquid water or ammonia water solution, kept from freezing by trace amounts of internal heat from radioactive decay, though this remains speculative for most. What is not speculative is the sheer number of these worlds. The Kuiper Belt contains more dwarf planet candidates than any other region of the solar system, and the actual total of large bodies almost certainly exceeds current catalogues by a wide margin. Most Kuiper Belt objects are faint, distant, and difficult to detect. Every new survey with improved sensitivity reveals additional members. The population count continues to grow. This concentration of worlds beyond Neptune forces a fundamental reconsideration of what the solar system actually is. The familiar inner system from Mercury to Neptune contains 8 major planets, a handful of dwarf planets, and a few 100,000 asteroids. The Kuiper Belt, by contrast, contains multiple dwarf planets, potentially hundreds of thousands of objects larger than 100 kilometers, and billions of smaller icy bodies. In terms of sheer population count, the outer solar system overwhelms the inner. The region most people ignore contains more individual worlds than the region most people study, and each one of these frozen bodies carries its own history, its own surface features, its own story written in ice and rock and ancient chemistry. Some spin rapidly, some have moons, some have rings, some may have atmospheres so thin they exist only as theoretical envelopes detected during rare stellar occultations. Some may have subsurface oceans locked beneath shells of frozen water, isolated from the universe for billions of years. These are not asteroids. They are not debris. They are worlds. Small, cold, distant, but worlds nonetheless. And the fact that they exist in such numbers, at such distances, in such variety, reveals something profound about the nature of planetary systems. Formation does not stop at a tidy boundary. The process that built the Earth also built Pluto, Eris, Makemake, and thousands of others. The same gravitational collapse, the same accretion of ice and rock, the same slow assembly over millions of years. The only difference is location. The inner system had enough material and enough time to build large planets. The outer system did not. But the process tried, and what it left behind was not failure. It was a population of frozen archives, each one preserving a snapshot of the conditions under which it formed. The Kuiper Belt is not the end of the solar system, it is a neighbourhood. Populated, diverse, and largely unexplored. And Pluto was never the lonely 9th planet. It was always the first known citizen of a community we are only now beginning to meet. There is a question that sits at the very foundation of planetary science, one so basic it seems like it should have been answered long ago. How does a planet begin? Not how does it grow large, not how does it develop an atmosphere or a magnetic field or a system of moons, but how does the very first solid body form from a cloud of gas and dust floating in space? For decades, the standard answer was gradual accumulation. Dust grains floating in the solar nebula collide gently, stick together, and build slowly into larger and larger clumps. Pebbles form from grains, boulders form from pebbles, kilometre-sized bodies form from boulders, and eventually, through billions of individual collisions, planetesimals large enough to exert meaningful gravity emerge and begin sweeping up material more efficiently. The process is slow, patient, and stepwise, like building a wall by placing one brick at a time. It seemed reasonable. It matched some observations, but it had a problem. At the scale of metre-sized bodies, the math breaks down. Objects that size are large enough to be destroyed by collisions, but not yet large enough for gravity to help them hold together. They exist in an awkward middle ground where growth stalls and destruction becomes equally likely. This is called the metre-size barrier, and for years it was one of the most stubborn, unsolved problems in planet formation theory. Then came a different idea, not gradual accumulation, but sudden collapse. The theory is called the streaming instability. It proposes that small solid particles in a protoplanetary disk do not need to stick together one by one. Instead, aerodynamic interactions between the particles and the surrounding gas cause them to drift together into dense, concentrated filaments. When these filaments reach a critical density, they become gravitationally unstable and collapse inward under their own weight. The collapse is fast by astronomical standards, happening over thousands rather than millions of years. And the result is not a single large body, but often a pair of bodies. Two gravitationally bound clumps that orbit each other closely before eventually spiraling together into contact. The outcome of this process is a contact binary. Two originally separate bodies, each one formed by its own gravitational collapse, joined at a narrow neck where they touched and froze together. Their shapes reflect their independent origins. Each lobe carries the form of a distinct collapsed cloud, rounded but not perfectly spherical, pressed together at a single junction point. For years, this theory existed in computer models and mathematical equations. The direct observational evidence that contact binaries were common in the Kuiper Belt came from Earth-based telescopes, measuring how the brightness of distant objects changes as they rotate. A contact binary, tumbling end over end in space, alternately presents its widest and narrowest profile to the observer. The resulting brightness variation follows a distinctive double-peaked pattern that round objects do not produce. Studies of these light curves suggested that a significant fraction of small Kuiper Belt objects, estimates range from 10 to 30%, may be contact binaries. But light curves from Earth are indirect evidence. What scientists needed was a close look. On the first day of January 2019, they got one. New Horizons, the same spacecraft that revealed Pluto's geological complexity in 2015, flew past a small Kuiper Belt object designated 486958 Arrokoth, orbiting in the cold classical belt at approximately 44 astronomical units from the Sun. Arrokoth is roughly 36 kilometers long and is composed of two flattened lobes connected at a narrow neck. The larger lobe, nicknamed Ultima, measures about 22 kilometers across. The smaller lobe, nicknamed Thule, measures about 14 kilometers. Together they form a shape that was immediately compared to a snowman, though the flatness of both lobes gives the object a more pancake-like profile than any snowman you might build on a winter afternoon. The images confirmed something extraordinary. Arrokoth did not form through a violent collision. The two lobes came together at speeds of only a few meters per second, slow enough that a person walking briskly could nearly match the pace. There were no signs of impact damage, no shattered edges, no signs of compression stress at the neck. The merger was gentle, quiet, almost tender. Two separate bodies that formed in close proximity orbited each other briefly and then spiraled slowly together until they touched and joined. This was exactly what the streaming instability model predicted. Two clumps condensing simultaneously from the same gravitational collapse, close enough to become gravitationally bound, slow enough in their relative motion to merge without destruction. Arrokoth was not just a contact binary, it was physical proof of the streaming instability mechanism, the first object in the solar system ever observed up close that could only be explained by this formation process. In February 2026, a study published in the monthly notices of the Royal Astronomical Society provided the most detailed computer simulations yet of how these shapes form. Jackson Barnes, a graduate student at Michigan State University, demonstrated through modelling that a spinning cloud of pebble-sized material can collapse, split into two gravitationally bound lobes, and then bring those lobes into gentle contact without shattering either one. The simulations produced a variety of two-lobed shapes with different proportions, matching the diversity of contact binaries observed throughout the belt. The results strengthened the case that objects like Arrokoth form directly as two-lobed structures, rather than assembling later through lucky low-speed collisions between independently formed bodies. The surface of Arakoth added another layer of information. At the resolution New Horizons achieved, the object showed almost no small craters. On most solar system surfaces, small impacts vastly outnumber large ones, peppering every exposed face with tiny pits at every scale. Arakoth's smooth surface suggested one of two things. Either the cold classical belt contains far fewer small impactors than models predicted, meaning the environment there is calmer than expected, or some process erases small craters over time. Either explanation carries significant implications for understanding the collision environment of the outer solar system. A separate finding added another dimension. In early 2025, observations from the Hubble Space Telescope revealed that a Kuiper Belt system previously identified as a binary, two objects orbiting each other, showed orbital dynamics consistent with a hidden third member too close to its companion to resolve visually. If confirmed, this would make it only the second known triple system in the Kuiper Belt. The streaming instability hypothesis predicts that gravitational collapse should naturally produce not just binary pairs, but also higher-order multiples. Finding triple systems validates that prediction and suggests many more exist throughout the belt, waiting for more sensitive instruments to find them. The implications of Arakoth extend far beyond the Kuiper Belt itself. If streaming instability and gravitational collapse are the dominant mechanisms for forming small bodies in the outer disk, the same processes likely operated throughout the entire early solar system. The building blocks that eventually assembled into the terrestrial planets may have begun not as individual grains sticking together one at a time, but as collapsed clouds forming binary pairs that gently merged. The story of how the Earth began may be written, in miniature, in the shape of a 36-kilometre snowman drifting through the frozen outer darkness. Every contact binary in the Kuiper Belt is a data point in the largest formation experiment in history, one that ran for 4.5 billion years with no observers, no instruments and no record keeping, until the moment a small spacecraft aimed carefully across 3 billion miles of empty space and finally arrived to look. What it found was not wreckage. It was a fossil of creation itself, preserved in the cold classical belt with a fidelity so complete that it arrived across the full span of cosmic time essentially unchanged. The solar system built its smallest pieces gently, not through violence, but through gravity and patience. And in the frozen outer darkness, those gentle first moments are still visible, waiting to be read by anyone willing to make the journey. There is a particular kind of humility that science demands at its best moments. The humility of arriving somewhere with a set of confident expectations and discovering that reality has prepared something entirely different, something richer, stranger, and more surprising than the models allowed. The New Horizons flyby of Pluto on July 14, 2015, was one of those moments, and what it revealed about a world that everyone assumed they already understood changed the entire conversation about what frozen outer solar system bodies are capable of. The expectation going in was almost universally pessimistic. Pluto is small, just 2,370 kilometers in diameter, smaller than Earth's moon. Its surface temperature hovers around minus 230 degrees Celsius. It sits roughly 40 astronomical units from the Sun, receiving light so faint it delivers almost no meaningful warmth. At that distance, with that size, and with no significant tidal forces from a nearby large body to generate internal heat, the dominant scientific prediction was straightforward. Pluto should be geologically dead. Its surface should be ancient, heavily cratered, battered by billions of years of impacts, and entirely unchanged for most of its existence. A frozen relic. The first high-resolution images ended that narrative permanently. New Horizons arrived at Pluto travelling at roughly 14 kilometers per second, far too fast to slow down and enter orbit. The entire encounter was a single high-speed flyby, the closest approach bringing the spacecraft within 12,500 kilometers of Pluto's surface. Every instrument aboard fired continuously during the pass, collecting data that would take over a year to transmit back to Earth at the speed of light. The signal confirming a successful flyby took 4 hours and 25 minutes to reach mission control at the Johns Hopkins Applied Physics Laboratory. What came back in the data described a world of staggering geological complexity. The western hemisphere of Pluto is dominated by a vast heart-shaped feature now officially named Tombor Regio, honouring Clyde Tombaugh, the astronomer who discovered Pluto in 1930. The left lobe of this heart contains a massive plain of nitrogen ice called Sputnik Planitia, a basin roughly 1,000 kilometers across and several kilometers deep. Sputnik Planitia is one of the smoothest surfaces ever observed anywhere in the solar system. It contains no visible impact craters. In a region of space where cratering should be the dominant surface process, a blank slate this large carries only one possible interpretation. The surface is geologically young. Something erased the craters. Something is still active. Scientists determined that Sputnik Planitia is a dynamic landscape. The nitrogen ice filling the basin is not static. It moves. The surface is divided into irregular polygonal cells, each roughly 30 to 40 kilometers across, separated by shallow troughs. These cells are the visible expression of convective overturn happening in the nitrogen ice beneath the surface. Warmer ice rises from the interior of the basin, spreads across the surface, cools and sinks at the edges, creating a slow churning motion similar to the pattern seen in gently heated liquid. The process operates on timescales of roughly 500,000 years per overturn cycle. Slow by human standards, but geologically vigorous for a world this cold and this remote. Around the edges of Sputnik Planitia, the landscape changes dramatically. Mountain ranges of water ice rise abruptly from the basin floor, reaching heights of 3 to 4 kilometers. At Kuiper Belt temperatures, water ice behaves mechanically like rock, rigid and strong enough to support steep slopes and sharp peaks. These mountains are not volcanic. They are blocks of water ice bedrock, standing like frozen sentinels along the margins of a glacial plain, structurally stable in conditions where everything else is either nitrogen frost or methane ice. Elsewhere on Pluto's surface, New Horizons found evidence of even greater geological diversity. Dark reddish patches near the equator are coated in tholins, the complex organic compounds produced when ultraviolet light breaks apart simple molecules in Pluto's thin atmosphere. Blade-like ridges of methane ice called penitente extend for hundreds of kilometers in some regions, their sharp profiles carved by sublimation patterns driven by the angle of the faint incoming sunlight. Impact craters of varying sizes mark much of the surface outside Sputnik Planitia, but even these show signs of modification, partially filled by ice deposits or cut through by tectonic fractures that cross the landscape in long sweeping lines. Those fractures are among the most telling features New Horizons observed. Long extensional faults stretch across Pluto's surface for hundreds of kilometers. These cracks indicate that Pluto's outer shell has been pulled apart by internal expansion. The most compelling explanation involves a subsurface ocean. If a layer of liquid water, possibly mixed with ammonia acting as a natural antifreeze, exists between Pluto's rocky core and its outer ice shell, that ocean would gradually freeze from the outside inward over geological time. Water expands when it freezes. As the ocean solidifies, the expanding ice pushes outward against the shell, generating tensional stress that eventually tears the surface apart along these fault lines. The possibility that Pluto harbours a subsurface ocean was among the most consequential findings of the entire mission. Thermal models developed after the flyby suggest that a layer of liquid water could persist beneath the ice shell to the present day, kept from freezing by residual radioactive heat from Pluto's rocky core. Faint, but sufficient, insulated from the minus 230-degree surface by kilometres of frozen nitrogen and water ice above it. If such an ocean exists, Pluto joins a growing list of solar system worlds, including Europa, Enceladus, Titan, and Ganymede, where liquid water may persist beneath an icy exterior far from the sun's warmth. The common thread connecting all of these worlds is not proximity to the sun. It is internal heat generated by radioactive decay or tidal forces. The sun is not the only energy source in the solar system, and the definition of a habitable environment, at least in the chemical sense, may be far broader than proximity to a star. Pluto's atmosphere added another dimension of surprise. The dwarf planet possesses a thin but real atmosphere composed primarily of nitrogen with traces of methane and carbon monoxide. The surface pressure is roughly 100,000 times lower than Earth's, barely above a technical vacuum. But this thin envelope of gas extends hundreds of kilometres above the surface, far higher than expected. New Horizons detected stacked layers of atmospheric haze visible in backlit images taken as the spacecraft looked back at Pluto after closest approach. These haze layers are composed of tiny tholin particles created by photochemical reactions in the upper atmosphere, particles that slowly settle toward the surface and contribute to the reddish deposits observed on the ground. Pluto's atmosphere also breathes seasonally. As the dwarf planet moves along its eccentric 248-year orbit, its distance from the Sun varies from about 29.7 astronomical units at closest approach to 49.3 at its farthest. This variation drives cycles in which surface ices sublimate into gas during relatively warmer periods and refreeze during colder ones. At Pluto's most distant orbital point, the atmosphere may collapse almost entirely, freezing out onto the surface as a thin frost layer before the long, slow approach back toward the Sun begins to warm it once more. The atmosphere rises and falls over centuries, a slow cosmic breath, measured not in seconds or hours, but in decades and generations of human time. What New Horizons found at Pluto was not the dead frozen relic that models predicted. It was a world with active geology, flowing glaciers, a dynamic atmosphere, towering mountains, and possibly a hidden ocean that has existed since before life appeared on Earth. A world smaller than the Moon, orbiting in one of the coldest and darkest regions of the solar system, doing things that nothing in its size range and location was supposed to be doing. The lesson is one that the Kuiper Belt has been teaching, in different forms since the first object was discovered there in 1992. The outer solar system does not behave the way we expect it to. It does not follow the simple rules that feel intuitive from the warm, bright vantage point of Earth. It has its own logic, its own energy sources, its own geological processes, operating on timescales and in conditions that have no earthly equivalent. And every time we arrive expecting emptiness, we find complexity waiting quietly in the dark. When New Horizons swept past Pluto in July 2015, it did not encounter one world, it encountered two. Charon, Pluto's largest moon, was not a passive backdrop to the main event. It was a destination in its own right, a world of its own character, its own geology, its own history, and its own set of surprises that proved almost as scientifically disorienting as the discoveries on Pluto itself. Begin with the basic geometry of the relationship between these two bodies, because it is unlike anything else known in the solar system. Charon has a diameter of roughly 1,212 kilometers, more than half the size of Pluto. The mass ratio between a moon and its parent body is typically enormous. Earth's moon, for example, has about 1/80th of Earth's mass. Charon has roughly 1/8th of Pluto's mass. This means the gravitational center around which both bodies orbit, a point called the barycenter, does not lie inside Pluto. It lies in empty space between the two worlds, about 900 kilometers above Pluto's surface. Both Pluto and Charon orbit this shared center of gravity. Neither one simply circles the other in the conventional sense. They are locked in a mutual gravitational embrace, each presenting the same face permanently toward the other, each completing one orbit every 6.4 Earth days. No other known planet-moon system in the solar system exhibits this mutual tidal locking. They move through space together like two dancers frozen in a permanent face-to-face rotation, separated by roughly 19,600 kilometers of empty vacuum, each one holding the other in gravitational attention across that silent gap. Scientists sometimes describe the Pluto-Charon system not as a planet and its moon, but as a binary world. Two bodies of comparable size sharing an orbit, connected by gravity rather than by any physical structure. The distinction matters because it changes how you think about their history. Two bodies this closely matched in size almost certainly share a common origin, and the leading theory points to a massive collision early in the solar system's history. An impact between a proto-Pluto and another large icy body that blasted material into orbit, and that orbiting material eventually coalesced into Charon. The scenario mirrors the giant impact hypothesis for the Earth-Moon system, scaled down and moved to the frozen outer wilderness. Charon's surface, as revealed by New Horizons, tells a story completely different from Pluto's. Where Pluto is coated in volatile nitrogen and methane ices that sublimate and migrate across the surface in seasonal cycles, Charon's surface is dominated by water ice, stable and chemically inert at these temperatures. The Moon lacks the bright dynamic frost fields that make Pluto visually striking. Instead, Charon presents a muted grey and brown landscape, older looking, more heavily cratered in some regions, quieter in its surface activity. A world that has settled into a kind of geological stillness that Pluto, surprisingly, has not. But Charon is far from featureless. Its north pole is capped by a dark reddish deposit that mission scientists informally named Mordor Macula. The colour and distribution of this deposit are unlike anything seen on Charon's other surface regions, and the explanation for its existence connects directly to its binary partner across the void. Methane molecules escaping from Pluto's thin atmosphere drift outward into space. Some of this methane reaches Charon's polar regions, where it becomes cold trapped on the surface during the decades-long polar winter, when those regions receive no sunlight at all. When the pole eventually rotates back into the faint light of the distant sun, ultraviolet radiation breaks apart the trapped methane molecules and triggers a cascade of chemical reactions that build increasingly complex organic compounds. Over millions of years, this repeated cycle deposits a progressively thicker layer of dark reddish tholins on Charon's poles. It is atmospheric chemistry, conducted across 19,000 kilometers of vacuum between two worlds. Pluto breathes out. Charon catches what drifts across. And the evidence accumulates on the pole over geological time, layer by layer, cycle by cycle, building a dark cap that records the history of an atmospheric relationship unlike anything observed elsewhere in the solar system. Charon's equatorial region delivered something even more dramatic. Stretching across the Moon's midsection is a vast canyon system running for over 1,000 kilometers and plunging to depths of up to 9 kilometers in some sections. To place that in perspective, Earth's Grand Canyon reaches a maximum depth of roughly 1.8 kilometers. Charon's rift system is 5 times deeper, cut across a world that is only about 1/10 the diameter of Earth. In terms of scale relative to the body it occupies, this canyon system is one of the most extreme geological features in the known solar system. The presence of such a massive extensional feature tells scientists that Charon's outer shell was subjected to tremendous stretching stress at some point in its past. The most compelling explanation mirrors the subsurface ocean hypothesis proposed for Pluto. If Charon once possessed an internal ocean of liquid water, the gradual freezing of that ocean over billions of years would have caused the interior to expand. Water, uniquely among common substances, expands when it freezes. As the ocean solidified from the outside inward, the growing volume of ice pushed outward against the overlying shell, stretching it beyond its elastic limit and tearing it apart along the equatorial zone. The canyon system would be the permanent scar of that ancient expansion, a record written in fractured ice across the face of a moon that by all conventional expectations should have been geologically silent from the day it formed. Small worlds in the outer solar system were not supposed to have enough internal heat to drive geological processes. Charon's canyon is evidence that this assumption was wrong. The possibility that both Pluto and Charon once harboured internal oceans and may still harbour remnant liquid layers today carries implications that extend far beyond these two specific bodies. Both are small. Both orbit in one of the coldest regions of the solar system. Both receive sunlight so faint it contributes nothing meaningful to their internal thermal state. And yet the evidence on both their surfaces points toward internal activity driven by nothing more than the slow, patient decay of radioactive elements in their rocky cores. Radioactive decay is not a dramatic energy source. It does not produce the spectacular heat that a nearby star generates, or the tidal forces that squeeze and flex the interiors of moons like Europa and Enceladus. It is quiet, steady, and remarkably long-lived. Certain radioactive isotopes incorporated into rocky material during the solar system's formation continue releasing heat today, 4.5 billion years later, at rates low enough to be easily overlooked, but high enough to matter when the surrounding environment is cold enough and insulating enough to trap that heat effectively. In the Kuiper Belt, where surface temperatures sit near -230 degrees, thick shells of frozen water and nitrogen ice act as extraordinarily effective thermal blankets. Even a tiny trickle of internal heat, trapped beneath kilometers of ice, may be sufficient to maintain a thin liquid layer at the base of the shell indefinitely. The ice above acts not as a barrier to life or chemistry, but as insulation, preserving conditions below that the extreme surface environment would otherwise destroy. If this mechanism operates on Pluto and Charon, it almost certainly operates on other large Kuiper Belt objects as well. Dozens of bodies comparable in size to Charon orbit in the same distant region. If even a fraction of them share similar internal thermal structures, the outer solar system may contain a far larger inventory of liquid water environments than anyone imagined before New Horizons arrived. Not warm, sunlit oceans open to the sky, but cold, dark, chemically rich liquid layers sealed beneath kilometers of ice, isolated from the universe, quietly preserving conditions that have persisted since before the first living thing appeared on Earth. Charon is not simply Pluto's companion. It is a world in its own right, carrying its own geological history, its own chemical relationship with its binary partner, and its own evidence of internal processes that should not exist but clearly do. The canyon across its equator is not a curiosity. It is a testament to a solar system that is consistently more active, more complex, and more surprising than the models built to describe it. Every scar on Charon's surface is a question waiting for an answer. And the deeper into the Kuiper Belt science looks, the more questions accumulate. There is a particular kind of scientific discovery that arrives not with a dramatic announcement or a single striking image, but with a quiet, persistent signal that refuses to behave the way the model said it should. No explosion, no sudden revelation, just a number that keeps coming out wrong, stubbornly and repeatedly wrong, until the only honest conclusion is that something out there is different from what everyone assumed. That is exactly how New Horizons rewrote the outer boundary of the solar system. The instrument responsible was not a camera. It was not a spectrometer or a magnetometer. It was a dust counter, a relatively simple device designed and built by students at the University of Colorado Boulder, named the Venetia Burney Student Dust Counter, in honor of the 11-year-old girl who suggested the name Pluto when the dwarf planet was discovered in 1930. The instrument works by measuring the rate at which microscopic dust particles strike the spacecraft as it moves through space. Each impact registers as a tiny electrical signal. Count enough signals over enough time, and you build a picture of how much dust exists in each region of space the spacecraft passes through. Dust in the outer solar system is not random contamination. It has a specific origin. It comes primarily from collisions between larger Kuiper Belt objects, and from particles released when those objects are struck by interstellar dust grains travelling in from outside the solar system. When two Kuiper Belt objects collide, even gently, they shed small fragments and microscopic particles that spread slowly through the surrounding space. The rate at which dust is produced depends directly on how many objects exist in a given region and how frequently they interact. More objects means more collisions. More collisions means more dust. Dust density, in other words, is a tracer of population density. This relationship formed the basis of a clear prediction. The main body of the Kuiper Belt, containing the highest concentration of known objects, occupies the zone between roughly 30 and 50 astronomical units. Beyond 50 astronomical units, telescope surveys from Earth detect fewer and fewer Kuiper Belt objects. The population appears to drop off sharply near that boundary, a feature that models of Neptune's gravitational influence had predicted, and that decades of observation seem to confirm. The outer edge of the Kuiper Belt was understood to sit near 50 astronomical units, and beyond that boundary, the solar system was expected to thin rapidly into something approaching genuine emptiness. As New Horizons moved outward through the Kuiper Belt after its Arakoth flyby in January 2019, the dust counter kept recording. The spacecraft was travelling into the region beyond 50 astronomical units, the zone where models confidently predicted the belt would be fading away. Dust production should have declined in step with the declining population. The instrument should have been registering fewer and fewer impacts as the spacecraft left the main belt behind and entered the emptier space between the Kuiper Belt and the hypothetical Oort cloud. Instead, the dust counter detected something that the models had not anticipated. Between approximately 45 and 55 astronomical units from the Sun, the dust levels remained elevated, higher than expected, higher than the known population of Kuiper Belt objects in that region could account for. The signal did not fade as predicted. It persisted, quietly but unmistakably, telling the instrument and the scientists monitoring its output that something was producing dust in a region where almost nothing was supposed to exist. The data, published in the Astrophysical Journal Letters in early 2024, presented scientists with two possible explanations, both of them significant. The first possibility is that the main Kuiper Belt extends much farther outward than current models estimate. Rather than dropping off sharply near 50 astronomical units, the population of icy bodies might continue at meaningful densities well beyond that boundary, perhaps stretching to 60, 70, or even farther from the Sun. The known objects detected by Earth-based telescopes may represent only the brightest, largest members of a population that continues into regions too faint and too distant for current surveys to reach. If this is correct, the outer edge of the Kuiper Belt is not where anyone thought it was, and the solar system's outer structure is simply larger than the standard model describes. The second possibility is even more striking. A separate, previously unknown population of icy bodies may exist beyond the classical belt, a distinct outer ring or extended debris field that produces its own dust through mutual collisions, entirely independent of the main Kuiper Belt. This hypothetical outer population would represent a new structural zone of the solar system, something that has no place in current models and whose existence would require a fundamental revision of how the outer solar system formed and evolved. Both explanations carry profound implications. An extended belt means the solar system's outer structure is larger than thought. A second belt means it is more complex than thought. Neither scenario was anticipated by the standard models that had guided Kuiper Belt science for decades, and the dust counter data, collected by a spacecraft instrument originally designed and built as a student project, may have been the first direct measurement to reveal this discrepancy. Alan Stern, the principal investigator of New Horizons, described the finding as potentially the first time any spacecraft had discovered a new population of bodies in the solar system entirely through in situ measurements rather than direct imaging. The statement carried appropriate scientific caution. Dust measurements alone cannot definitively distinguish between an extended belt and a separate outer population. The dust grains themselves carry no return address. They arrive as impacts on the detector, registering as counts and particle sizes without revealing their precise origin. But the data represents something no telescope on Earth can provide, a direct physical measurement from inside the region being studied. No other spacecraft has ever operated scientific instrumentation in this part of the outer solar system. New Horizons is the only probe currently collecting original data from within and beyond the Kuiper Belt, and its readings are consistently telling scientists that the belt is not fading away as the models predicted. Something is out there, producing dust, maintaining collision rates, extending the structure of the outer solar system into regions that remain almost entirely unmapped by any survey from Earth. The Vera Rubin Observatory, which recently began operations in Chile and carries the largest digital camera ever built for astronomy, is expected to discover approximately 35,000 new Kuiper Belt objects over the next decade, nearly a tenfold increase in the known population. These discoveries will dramatically improve the census of the outer solar system, revealing fainter and more distant objects, filling in the size distribution, and potentially identifying whether the dust signal detected by New Horizons corresponds to a known extended population or something genuinely new. But even this dramatic expansion in knowledge will face fundamental limits. The Kuiper Belt is not a thin ring. It is a thick, three-dimensional torus of space extending above and below the plane of the solar system. Its total volume is staggering. If you calculated the cubic volume of space enclosed between 30 and 50 astronomical units around the Sun, the number would carry more zeros than most calculators can display. For perspective, the volume of space enclosed by Earth's orbit around the Sun is approximately 3.4 times 10 to the 24th cubic kilometers. The Kuiper Belt's volume is roughly 100,000 times larger than that, 100,000 times more space than the entire sphere containing Earth's yearly path around the Sun. In a volume that large, even hundreds of thousands of objects are separated by distances so vast that the belt is overwhelmingly empty space. And in empty space that vast, a dust signal that should not be there is not a small anomaly. It is a frontier marker. A signal from a region humanity has never physically entered, pointing towards structure we have not yet mapped, in a solar system that continues to be larger, stranger, and more surprising than the models built to describe it. The dust counter keeps counting, the signal persists, and somewhere beyond 50 astronomical units, in the cold dark that no telescope has fully mapped and no spacecraft has deliberately explored, something is out there making dust. There is a kind of loneliness that has no human equivalent. Not the loneliness of being far from home, or separated from people you care about, or stranded somewhere unfamiliar. Those are conditions measured in miles and hours and the possibility of return. The loneliness of the Kuiper Belt is something deeper and more absolute. It is the loneliness of existing in a volume of space so vast that your nearest neighbour, a body of comparable size, sits tens of millions of kilometres away, separated from you by a void so complete that you could look in every direction with the most powerful telescope imaginable and see nothing but stars and darkness. This is the Kuiper Belt's most disorienting characteristic, and it is the one that diagrams fail entirely to communicate. When you see an illustration of the belt, the objects appear clustered together, packed into a dense band surrounding the sun like gravel on a ring road. The visual impression is of a crowded region, thick with material, busy with bodies drifting close enough to see one another. The reality is the opposite. The Kuiper Belt is overwhelmingly, incomprehensibly empty, and the distances between its objects are so vast that each one exists in a state of total isolation, connected to the others only by mathematics and orbital mechanics, never by anything visible, tangible, or immediate. Consider the numbers plainly. The average separation between large Kuiper Belt objects, those larger than 100 kilometres across, is estimated to be on the order of tens of millions of kilometres. For context, the entire distance between Earth and Mars at their closest approach is roughly 34 million kilometres. That is the gap between neighbouring Kuiper Belt objects. Each one drifts through its own private expanse of nothing, separated from the next by a void wide enough to swallow the full orbital distance between two inner planets. New Horizons experienced this emptiness directly. After its flyby of Pluto in July 2015, the spacecraft continued outward through the Kuiper Belt, travelling at roughly 14 kilometres per second. For the next 3.5 years, it flew through the heart of the most populated region of the outer solar system without encountering anything. No objects came within imaging range. No bodies passed close enough to alter the spacecraft's trajectory even slightly. The probe moved through billions of cubic kilometres of space occupied, in theory by thousands of Kuiper Belt objects, and saw nothing but empty vacuum. It was not until January 2019, after years of painstaking telescope searches from Earth to identify a suitable target along the spacecraft's very narrow path, that New Horizons finally passed within 3,500 kilometres of Arrokoth, a body roughly 36 kilometres long, embedded in a region where the nearest comparable object might be 50 million kilometres away or more. The spacecraft threaded a needle across billions of miles of travel to reach a single tiny target drifting in a wilderness so vast that missing it by even a fraction of a degree would have sent the probe sailing through nothingness for years without encountering anything at all. This sparsity is not incidental, it is fundamental. The volume of space occupied by the Kuiper Belt is so staggeringly large that even a population numbering in the hundreds of thousands or millions of objects cannot fill it in any meaningful sense. The belt's volume, stretching from 30 to 50 astronomical units around the Sun in a thick three-dimensional torus, is roughly 100,000 times larger than the volume of space enclosed by Earth's orbit. Imagine taking the entire sphere that contains Earth's yearly journey around the Sun, a volume already so vast that light itself needs 8 minutes to cross from centre to edge, and multiplying it by 100,000. That is the Kuiper Belt. a region so voluminous that the entire orbital sphere of Earth vanishes inside it, the way a drop of water vanishes inside a tanker truck, and most of that volume is vacuum. Pure, unbroken, featureless vacuum separating objects that will never interact, never approach each other, never exert any influence on one another, except through the faint, patient mathematics of gravity acting across distances that human perception cannot hold. Compare this to the inner solar system, where the psychological experience of space is entirely different. From Earth, you can see Venus, Mars, Jupiter, and Saturn with your unaided eyes. The moon dominates the night sky, close enough that its surface features are visible without a telescope. Ancient civilizations tracked planetary motions and built cosmologies around what they observed. The inner solar system feels populated. Objects are bright enough, close enough, and interactive enough that celestial neighbours are part of everyday human experience. In the Kuiper Belt, that entire framework collapses. There are no naked eye neighbours. There is no bright wandering object to track across the seasons. There is no nearby moon to light the landscape. If you stood on the surface of a Kuiper Belt object and looked up, you would see stars. Thousands of them, blazing with a clarity impossible on Earth because there is no atmosphere to scatter their light. And among those stars, if you knew exactly where to look, you would find the sun, reduced to a single brilliant point indistinguishable in apparent size from the brighter stars surrounding it. It would still be the brightest object in the sky, but it would no longer look like a sun. It would look like a very bright star, stripped of its warmth, stripped of its authority, stripped of everything that makes it feel like the centre of anything. The emptiness extends in every direction without variation. No horizon, no landmark, no way to gauge distance or position without instruments. The inner solar system, for all its vastness, provides a sense of place. You can look up from any inner planet and see evidence that you belong to a system, a structured collection of objects sharing a gravitational neighbourhood. The Kuiper Belt provides no such comfort. Its objects are so widely separated that each one exists in a private cosmos of empty space, connected to its neighbours only by invisible forces, never by anything you could see or touch or feel. This is not the kind of emptiness you experience on a dark night in the countryside, where at least the air around you carries sound and warmth, and the reassuring presence of a nearby surface beneath your feet. This is not even the emptiness of interplanetary space closer to the sun, where the planets still shine as bright points and the sun still blazes overhead. The emptiness of the Kuiper Belt is something more total. It is emptiness on a scale that eliminates context, emptiness that stretches so far in every direction that the structures anchoring human perception of space begin to dissolve entirely. Each Kuiper Belt object drifts through this wilderness alone, rotating slowly, orbiting the distant sun on a path that takes centuries to complete, separated from every comparable body by gulfs measured not in thousands of kilometres but in tens of millions. For 4.5 billion years, these objects have occupied this state. No visitors, no encounters, no change except the slow accumulation of cosmic ray damage on their surfaces and the faint chemical processing of surface ices by ultraviolet light from a sun too distant to provide any warmth. The mental image most people carry of the Kuiper Belt, the one shaped by diagrams and illustrations, suggests a region filled with objects. The truth is the opposite. The Kuiper Belt is a region defined by absence, a wilderness where each frozen world exists in a solitude so complete it has no terrestrial comparison. And that solitude is not temporary. It is the permanent, unbroken condition of existence in the outer solar system. The Kuiper Belt does not bring its worlds together. It holds them apart. and in that vast, patient separation, each one waits alone in the dark. There is a category of visitor that arrives in the inner solar system without warning, unannounced, glowing faintly in the night sky as it sweeps past the sun and then vanishes back into the darkness from which it came. For thousands of years, humans watched these apparitions with a mixture of fear and wonder, interpreting them as omens, as celestial warnings, as objects fundamentally different from the orderly planets that followed predictable paths across the sky. They called them comets, from the Greek word meaning long-haired, a reference to the streaming tails that stretch behind them as they move. For most of history, no one knew where comets came from. They appeared, brightened, faded and disappeared, some never to return, others arriving again after decades or centuries on schedules that seemed almost deliberate. It was not until the development of orbital mechanics in the 17th and 18th centuries that astronomers began to understand comets as natural members of the solar system, objects following elliptical paths around the sun just like the planets, only on trajectories far more elongated and eccentric. But even with the mathematics in place, the question of origin remained unanswered. Where do comets live when they are not visible? Where do they spend the centuries between their brief passages through the inner solar system? The answer for a specific class of comets lies in the Kuiper Belt. And the connection between these two populations, one frozen and distant, the other bright and active, reveals something profound about how the outer solar system continues to influence the chemistry and evolution of worlds much closer to the Sun. Short-period comets, specifically the Jupiter family comets that return to the Sun's vicinity on timescales of roughly 20 years or less, originate primarily from the Kuiper Belt. Familiar examples include Comet Tempel 1, visited by NASA's Deep Impact mission, and Comet 67P Churyumov-Gerasimenko, orbited and studied in detail by the European Space Agency's Rosetta spacecraft. Dozens of these comets have orbits consistent with Kuiper Belt origins, and the physical and chemical characteristics observed on their surfaces match what scientists expect from objects that spent billions of years in the frozen outer regions before being gravitationally nudged inward. The mechanism works like a slow, patient conveyor belt. Neptune's gravity occasionally destabilizes Kuiper Belt objects near the inner edge of the belt, nudging them onto orbits that cross Neptune's path. From there, gravitational encounters with the giant planets can progressively alter the object's trajectory over millions of years, pulling its closest approach to the Sun inward bit by bit. Eventually, the object enters the inner solar system, where solar radiation begins to activate its surface volatiles, and the transformation from frozen Kuiper Belt object to active comet begins. The transformation itself is violent and strange. For billions of years, the object drifted in the deep freeze of the outer solar system, its surface locked at temperatures near -230 degrees Celsius, its volatile ices sealed beneath a crust of radiation-processed organic material. Nothing happened to it. Nothing changed. Then, over the course of millions of years, its orbit slowly tightens. Each pass brings it fractionally closer to the Sun. At first, the additional warmth is negligible, a few fractions of a degree spread across centuries, but as the orbit contracts, the effect accumulates. Somewhere around 5 to 10 astronomical units from the Sun, roughly the distance of Jupiter to Saturn, the surface temperature begins to rise enough for the most volatile ices to respond. Carbon monoxide sublimates first, escaping directly from solid to gas without ever becoming liquid. Then carbon dioxide. Molecules that have been frozen solid since before the Earth existed begin to stir, transitioning from ice to vapor and venting into space through cracks and pores in the surface crust. As the object crosses inside Jupiter's orbit, the transformation accelerates. The Sun's radiation, now hundreds of times stronger than anything the object experienced in the Kuiper Belt, penetrates the dark surface layer and reaches the buried volatile ices beneath. Gas erupts through fissures and vents, carrying dust particles with it in jets that spray outward into the vacuum. The object develops a coma, a diffuse cloud of gas and dust surrounding the nucleus, glowing faintly in reflected sunlight. As it continues inward, solar wind and radiation pressure push the coma's material into long streaming tails, one made of ionized gas pointing directly away from the Sun, another made of dust curving gently along the orbital path. The comet has awakened. After 4.5 billion years of frozen stillness, it is being dismantled by the very star that created it. This process means that the comets visible from Earth are not exotic intruders from outside the solar system. They are messengers from the Kuiper Belt, carrying icy material that has been stored at near absolute zero temperatures for billions of years. When a comet's tail streams across the night sky, you are watching ancient Kuiper Belt ice sublimate in real time, releasing molecules that condensed from the solar nebula before the planets finished forming. The chemistry locked inside these bodies is primordial, preserved in the cold outer darkness and delivered intact to the inner solar system where instruments can study it up close. The importance of this delivery extends beyond scientific curiosity. During the period of heavy bombardment roughly 4 billion years ago, when the giant planet's migration was scattering icy bodies inward, a rain of cometary material fell on the young Earth. Some scientists propose that a significant fraction of Earth's water may have been delivered by cometary impacts during this era. The isotopic ratios of hydrogen measured in some comets match the ratios found in Earth's oceans, though the evidence remains debated and complicated by contributions from other sources such as water-rich asteroids from the inner solar system. Whether or not comets delivered most of Earth's water, the broader point stands. The Kuiper Belt is not isolated. It is not disconnected from the rest of the solar system. It is a reservoir that has been feeding material inward for billions of years, shaping the chemistry of the inner planets, possibly contributing to the conditions that allowed life to emerge on Earth. The frozen outer wilderness and the warm inner cradle are not separate systems. They are connected by gravitational mechanics and by the slow, steady rain of icy bodies nudged from their distant orbits and sent tumbling toward the Sun. Every comet that brightens in Earth's sky carries with it the chemical fingerprint of the Kuiper Belt. Water ice, methane, ammonia, carbon monoxide. Complex organic molecules formed by radiation processing over billions of years. These are not random contaminants. They are the same materials that once coated the cores of the giant planets, the same ices that, under different circumstances, might have contributed to building another world. The Kuiper Belt preserves these ingredients in deep freeze and delivers them, periodically and unpredictably, to the inner solar system, where they arrive as visitors from the ancient past. The comets you see are not strangers. They are pieces of the outer solar system, temporarily displaced, briefly illuminated, carrying messages written in ice and organic chemistry from a region most people will never see and most spacecraft will never reach. They are the Kuiper Belt made visible. Frozen time capsules opened by the heat of the Sun, releasing into the warm inner system the chemistry of a colder, older, more distant place. And when their ices are exhausted, when the volatiles have all sublimated away and nothing remains but a dark inert core of rock and dust, these comets become indistinguishable from asteroids. Silent. Dim. No longer messengers, just remnants of a journey that began billions of miles away in the frozen outer wilderness and ended in the bright warm chaos near the sun. They fade, they fall silent. But the Kuiper Belt remains, patient and cold, holding billions more in reserve, waiting for the next gravitational nudge to send another one inward toward the light. There is a moment, if you sit long enough with everything the Kuiper Belt has shown us, when the familiar picture of the solar system begins to feel different. Not wrong exactly, but incomplete in a way that changes the meaning of everything within it. The 8 planets, the asteroid belt, the rings of Saturn catching sunlight, the moons of Jupiter with their hidden oceans, all of it still real, still beautiful, still scientifically extraordinary, but now surrounded, embedded in something so much larger, so much colder, and so much older that the familiar part begins to look less like the solar system and more like a warm, well-lit room at the centre of a mansion whose true extent stretches into frozen darkness in every direction. The Kuiper Belt is where that darkness begins, not at the edge of the sun's gravitational reach, not at the theoretical boundary of the Oort cloud. Right there, just past Neptune, barely beyond the last familiar landmark, the solar system transforms into something fundamentally different from what the diagrams suggest. Something colder, something stranger, something that has no place in the mental model most people carry of their cosmic home. Begin with what that model actually contains. For most people, the solar system is a story with a clear structure. A bright central star, 4 rocky inner planets, a belt of asteroids, 4 giant outer planets, and somewhere at the far edge, small and cold and distant, Pluto. The story feels complete. The characters have names. The major regions have been visited by spacecraft. Photographs exist of every planet. The whole picture carries the quiet confidence of something finished and understood. But the Kuiper Belt dismantles that confidence permanently. Because the region most people think of as the solar system, the planetary zone from Mercury to Neptune, covers approximately 30 astronomical units of radial distance. The Kuiper Belt's main body alone adds another 20 astronomical units beyond that. The scattered disk extends to 100 astronomical units, and beyond the scattered disk, stretching from roughly 2,000 to 100,000 astronomical units from the Sun, lies a structure called the Oort cloud. The Oort cloud has never been directly observed. No telescope has ever resolved an individual object within it. Its existence is inferred from the orbits of long-period comets, which arrive from random directions with orbital periods stretching into millions of years. These comets must originate from a vast, roughly spherical reservoir at extreme distances, and the Oort cloud is the name given to that reservoir. Estimates of its population range from several hundred billion to a few trillion icy objects. Its outer edge, at 100,000 astronomical units, stretches more than 1.5 light-years from the Sun. The nearest star to the Sun, Proxima Centauri, lies just over 4 light-years away. The Oort cloud, at its outermost boundary, reaches more than 1/3 of the way to the nearest neighbouring star system. The solar system, properly defined to include all gravitationally bound material, is not the compact arrangement of planets and rings and moons that fits on a classroom poster. It is a structure measured in light-years, a sparse, frozen halo of icy debris extending so far from the Sun that the Sun's own gravity barely holds the outermost members in place. A passing star or a gravitational nudge from the Milky Way's disk can dislodge Oort cloud objects from their orbits, sending them tumbling inward on million-year journeys toward the inner solar system, or outward into interstellar space forever. The Kuiper Belt sits at the innermost margin of this vast outer domain. It is the last structured region, the last place where distinct dynamical populations and orbital resonances can be mapped and studied. Beyond it, the scattered disk thins into a diffuse haze, and beyond that, the Oort cloud stretches into theoretical territory that may never be directly observable with current or near-future technology. If you could shrink the solar system so that the Oort cloud's outer boundary fit inside a sphere the size of a football stadium, the entire planetary system from Mercury to Neptune would occupy a volume no larger than a tennis ball sitting at the centre of the field. The Kuiper Belt would be a thin shell just outside that tennis ball, barely visible from where the stadium walls begin. Everything humans have ever visited, every planet photographed, every moon mapped, every asteroid sampled, every spacecraft destination in the entire history of space exploration would fit inside an object you could hold in your hand, centered at the midpoint of a structure so large its walls would be invisible from where you stand. Consider what this means through the lens of the only spacecraft humanity has ever sent into this outer wilderness. New Horizons was launched in January 2006 aboard an Atlas V rocket, leaving Earth faster than any spacecraft before it. It crossed the orbit of the Moon in just 9 hours. It passed Mars's orbit in less than 3 months. It reached Jupiter in 13 months, and used the giant planet's gravity to slingshot itself toward the outer solar system. After 9.5 years of flight, it arrived at Pluto. After 13 years, it passed Erakoth. As of 2026, it has been travelling for 20 years at speeds exceeding 14 kilometers per second, and has reached approximately 64 astronomical units from the Sun. It is expected to exit the Kuiper Belt in 2028 or 2029, roughly 22 to 23 years after launch, and yet at that point it will have crossed only the innermost fringe of the Sun's true outer domain. The Oort cloud begins at roughly 2,000 astronomical units. At its current speed, New Horizons will not reach the inner edge of the Oort cloud for approximately another 700 years. It will not reach the outer edge for roughly 30,000 years. The fastest spacecraft ever launched from Earth will spend 7 centuries merely approaching the threshold of the solar system's true boundary and 30,000 years crossing it. That is the scale of what surrounds the familiar solar system. And the Kuiper Belt is simply the doorstep. It is the zone where the warm, ordered planetary system gives way to the sparse, frozen, unimaginably vast outer wilderness that constitutes the true bulk of the Sun's gravitational kingdom. The familiar solar system, every planet, every moon, every ring, every volcanic surface, every hidden ocean, every mapped and named and photographed feature of the worlds humans have studied for millennia, occupies a small, warm, bright clearing at the centre of a structure whose real dimensions stretch across light years of frozen silence. And that clearing, the one where Earth orbits, where the sun warms your skin, where seasons change and oceans move and living things go about their brief and complicated existences, is genuinely extraordinary precisely because of what surrounds it. The Kuiper Belt is not a threat. It is not an enemy. It is not a darkness that diminishes the warmth of the inner solar system. It is context, the vast, cold, ancient context that makes the warmth of Earth not merely comfortable, but cosmically remarkable. Most of the solar system is frozen. Most of it is dark. Most of it has never been touched by warmth, never hosted chemistry complex enough to become life, never produced anything as improbable and fragile and astonishing as a living world. The Kuiper Belt preserves that frozen majority in silent, patient suspension, holding the original ingredients of the solar system in a state of near-perfect cold storage, occasionally sending emissaries inward in the form of comets, quietly recording in its orbital architecture the history of a violent and chaotic early solar system. And Earth, this small warm planet orbiting in the bright inner clearing, is the exception, the anomaly. the place where the ingredients came together at the right temperature, in the right configuration, with the right chemistry, for long enough that something extraordinary happened. Life, consciousness. The capacity to look outward from this warm clearing, past the familiar planets, past the asteroid belt, past the gas giants, past Neptune, and into the Kuiper Belt beyond. And to understand, at least partially, what is out there and what it means. The solar system you thought you knew was always a small campfire burning at the centre of an enormous frozen night. The Kuiper Belt is where that night begins, and the night stretches on for billions of miles in every direction, cold and dark and ancient and full of frozen worlds that have been waiting, patiently and silently, since before the first living thing drew breath on the warm small planet closest to the fire. And so we return, gently, from the frozen outer darkness to the warmth that surrounds you now, from the silent isolation of worlds separated by tens of millions of kilometers to the simple, quiet reality of air on your skin and gravity holding you softly to the ground. The Kuiper Belt is real. It is out there, right now, 4 billion miles from where you sit, cold and ancient and impossibly vast. And yet you are part of the same system, formed from the same cloud of gas and dust, orbiting the same star. The frozen outer wilderness and this warm inner clearing belong to the same story. A story 4.5 billion years long, still unfinished, still unfolding, still full of surprises waiting in the dark. Rest now. You are home. And home, as the Kuiper Belt quietly reminds us, is rarer and more precious than the scale of the cosmos might suggest.